unbalanced current between phases in a Y or delta transformer with the neutral bonded to earth can lead to several issues. Firstly, heating in the transformer occurs due to the increased current flowing through the neutral winding, causing it to overheat. Secondly, voltage distortion can arise as the unbalanced current distorts the voltage on the delta side, affecting sensitive equipment. Thirdly, stray voltage may appear on the grounding system due to inadequate grounding practices, exacerbated by the unbalanced current. Y transformers offer advantages over delta transformers. One advantage is lower voltage on the secondary side, making them suitable for specific applications. 2. Improved voltage regulation is achieved because Y transformers maintain more stable voltage on the secondary side under varying loads. 3. Ground fault detection is easier with Y transformers due to the neutral point which can be grounded. Large unbalanced currents in Y transformers can have consequences. One is increased transformer losses, which reduce efficiency and lifespan. 2. Reduced transformer capacity means the transformer cannot deliver the same power as with balanced loads. 3. Transformer damage may occur where severe unbalanced currents damage windings or insulation, leading to failure. Phase-to-ground faults in Y transformers can cause problems. One is high fault current, due to the neutral being bonded to earth. A direct path to ground is created, resulting in very high fault currents that damage equipment and pose a safety hazard. 2. Voltage instability, where the fault current causes voltage fluctuations on other phases affecting sensitive equipment. 3. Transformer damage, where prolonged phase-to-ground faults damage the windings or insulation, potentially leading to failure. The unbalanced current flowing from neutral to earth can certainly contribute to stray voltage, especially if grounding isn't effectively implemented. Regarding the advantage of Y over delta transformer connections, aside from the potential for lower or higher voltage adjustments, Y connections offer a distinct advantage in terms of grounding. Specifically, the grounded neutral point in a Y system allows for effective ground fault protection. This means that in the event of a ground fault, a large current will flow back to the source through the grounding path, which can be easily detected by protective devices such as circuit breakers or ground fault relays. This rapid detection and isolation of ground faults helps to minimize damage to equipment and reduce the risk of electrical shock to personnel. In contrast, delta-connected systems typically do not have a neutral point that is directly grounded. This makes ground fault detection more challenging and often requires more sophisticated protection schemes. Furthermore, the absence of a grounded neutral in a delta system can lead to overvoltages during ground faults, which can further stress the insulation of electrical equipment. If there's a large unbalanced current, this can indeed contribute to several issues in the transformer's operation. Firstly, the unbalanced current will cause increased losses in the transformer windings, which leads to higher operating temperatures and reduced efficiency. Secondly, the unbalanced current can create voltage imbalances on the secondary side of the transformer, which can negatively impact the performance of connected loads. Thirdly, the unbalanced current can contribute to increased neutral current, which can overload the neutral conductor and potentially create a fire hazard. When a phase-to-ground fault occurs in a Y-connected transformer with the neutral bonded to earth, a large fault current will flow through the grounding path. This high fault current can cause significant damage to equipment if it's not quickly interrupted by protective devices. The magnitude of the fault current depends on several factors, including the source impedance, the transformer impedance, and the impedance of the grounding path. It's crucial to ensure that the grounding system is properly designed and installed to safely handle these fault currents. The grounding system should have a low impedance path back to the source to minimize the voltage rise during a fault and to facilitate the operation of protective devices. The equipment grounding conductors should be sized according to the National Electrical Code, NEC Table 250.122, to ensure that they can safely carry the available fault current. In addition, the overcurrent protective devices, such as circuit breakers or fuses, should be properly coordinated to quickly clear the fault and minimize the duration of the fault current. This coordination helps to prevent damage to equipment and reduce the risk of electrical shock. The unbalanced current between phases in a Y or delta transformer, with the neutral bonded to earth is influenced by several factors related to the transformer's construction, operation, and the connector's load. These factors include the impedance of the transformer windings, the type of core material used, the method of winding construction, and the characteristics of the connected load. The impedance of the transformer windings plays a crucial role in determining the magnitude of the unbalanced current. Higher impedance windings will tend to limit the flow of unbalanced current, while lower impedance windings will allow for greater unbalanced current flow. The type of core material used in the transformer also affects the unbalanced current. Core materials with higher permeability will tend to reduce the unbalanced current, while core materials with lower permeability will allow for greater unbalanced current flow. The method of winding construction can also impact the unbalanced current. For example, transformers with interleaved windings tend to have lower unbalanced currents compared to transformers with non-interleaved windings. The characteristics of the connected load have a significant impact on the unbalanced current. Nonlinear loads such as electronic devices and variable frequency drives can generate harmonic currents that contribute to unbalanced current flow. In addition, unbalanced single-phase loads can also cause unbalanced current in the transformer. The relationship between the stray voltage and unbalanced current can be complex and is influenced by several factors. These factors include the impedance of the grounding system, the distance between the transformer and the load, the presence of other electrical equipment, and the grounding practices employed. The impedance of the grounding system plays a crucial role in determining the magnitude of the stray voltage. Higher impedance grounding systems will tend to result in higher stray voltages, while lower impedance grounding systems will tend to reduce stray voltages. The distance between the transformer and the load can also affect the stray voltage. Longer distances will tend to increase stray voltage due to the increased impedance of the grounding conductors. The presence of other electrical equipment can also contribute to stray voltage. For example, equipment with poor grounding practices or equipment that generates harmonic currents can increase the stray voltage in the system. The grounding practices employed also have a significant impact on the stray voltage. Proper grounding practices, such as using a dedicated equipment grounding conductor and bonding all metallic components, can help to reduce stray voltage. The advantages of a Y transformer over a delta transformer connection extend beyond just voltage adjustments. Y connections offer several advantages that make them suitable for a wide range of applications. Firstly, Y connections provide a more stable and balanced voltage supply. This is because the neutral point in a Y system is typically grounded, which helps to maintain a consistent voltage reference and minimize voltage fluctuations. Secondly, Y connections offer better ground fault protection. A grounded neutral point allows for easy detection and isolation of ground faults, which helps to protect equipment and personnel. Thirdly, Y connections are more efficient than delta connections. This is because the current is distributed more evenly in a Y system, which reduces losses and improves overall efficiency. Y connections are commonly used in distribution systems, where a stable and reliable voltage supply is essential. They are also used in industrial applications, where ground fault protection is critical. In addition, Y connections are often used in step-down transformers, where a low voltage is required for specific applications. The effects of large unbalanced current on transformer operation can be severe and can lead to significant problems. Firstly, the unbalanced current can cause increased losses in the transformer windings, which results in higher operating temperatures and reduced efficiency. Secondly, the unbalanced current can create voltage imbalances on the secondary side of the transformer, which can negatively impact the performance of connected loads. Thirdly, the unbalanced current can contribute to increased neutral current, which can overload the neutral conductor and potentially create a fire hazard. In addition to these problems, large unbalanced currents can also shorten the lifespan of the transformer and increase the risk of catastrophic failure. To mitigate the effects of unbalanced current, it's important to ensure that the loads connected to the transformer are balanced as much as possible. This can be achieved by distributing the loads evenly across the phases and by using single-phase loads that are designed to minimize unbalanced current. It's also important to monitor the transformer for signs of unbalanced current and to take corrective action if necessary. This may involve adjusting the loads, upgrading the transformer, or implementing other measures to reduce the unbalanced current. The effects of a phase-to-ground fault on a Y transformer with the neutral bonded to earth can be significant and can lead to serious consequences. Firstly, the fault current can cause severe damage to equipment. The high fault current can quickly overheat and damage the transformer windings, conductors, and other components. Secondly, the fault current can create dangerous touch potentials. The voltage rise in the grounding system can create a hazardous voltage potential between grounded equipment and the surrounding environment. Thirdly, the fault current can cause widespread power outages. The fault current can trip protective devices, such as circuit breakers or fuses, which can interrupt power to a large area. In addition to these consequences, a phase-to-ground fault can also increase the risk of electrical shock to personnel. The fault current can flow through the body if a person comes into contact with energized equipment, which can result in serious injury or death. To mitigate the effects of a phase-to-ground fault, it's important to ensure that the grounding system is properly designed and installed. The grounding system should provide a low impedance path back to the source to minimize the voltage rise during a fault and to facilitate the operation of protective devices. It's also important to use ground fault protection devices such as ground fault circuit interrupters and ground fault relays to quickly detect and interrupt ground faults. These devices can significantly reduce the risk of damage to equipment and injury to personnel. The concept of stray voltage, particularly in relation to electrical systems and grounding, is multifaceted. Firstly, stray voltage, also referred to as neutral to earth voltage, arises from various sources within electrical distribution systems. These sources encompass unbalanced loads, inductive coupling, and capacitive coupling. Unbalanced loads, for instance, occur when electrical loads are not evenly distributed across the phases of a three-phase system, leading to current flow in the neutral conductor and subsequent voltage drop along the grounding path. Inductive coupling takes place when current-carrying conductors induce voltage in nearby metallic objects such as water pipes or fences, while capacitive coupling involves the transfer of electrical charge between conductors separated by an insulating material, resulting in voltage buildup. Secondly, the effects of stray voltage on equipment and living organisms vary based on the voltage magnitude and duration of exposure. Low levels of stray voltage might cause minor annoyance or discomfort, whereas higher levels can result in equipment malfunction, reduced productivity, and even health issues. For instance, in agricultural settings, stray voltage can impact livestock behavior and milk production, leading to economic losses for farmers. Thirdly, mitigating stray voltage entails adopting appropriate grounding techniques and employing specialized equipment. Proper grounding ensures a low impedance path for fault currents, minimizing voltage buildup on grounded surfaces. Copotential planes constructed by bonding metallic objects together create a uniform voltage zone to reduce the risk of electric shock. Furthermore, isolation transformers can be used to isolate sensitive equipment from the effects of stray voltage, while filters can mitigate harmonic currents contributing to stray voltage. Fourthly, regulatory standards and guidelines dictate the permissible levels of stray voltage in different environments. These standards, established by organizations like the Institute of Electrical and Electronics Engineers (IEE) and the National Electrical Code (NEC), aim to safeguard individuals and equipment from the detrimental effects of stray voltage. Compliance with these standards necessitates thorough testing and monitoring of electrical systems to identify and rectify stray voltage issues. In conclusion, stray voltage is a complex phenomenon with diverse causes and effects, necessitating a comprehensive approach to mitigation and management. By understanding the underlying principles and implementing appropriate measures, electrical professionals can ensure the safe and reliable operation of electrical systems while minimizing the risks associated with stray voltage. The factors that influence stray voltage in electrical systems are manifold. Grounding impedance is a primary factor, as high impedance in the grounding system allows voltage to accumulate on grounded surfaces. Load balancing is another critical aspect, as unbalanced loads contribute to neutral current and subsequent voltage drop along the grounding path. Harmonic currents, generated by nonlinear loads, can also exacerbate stray voltage issues. The physical layout of electrical systems, including conductor spacing and proximity to metallic objects, influences inductive and capacitive coupling, contributing to stray voltage. Furthermore, the presence of underground utilities and soil conditions can affect the distribution of stray voltage. The design and implementation of grounding systems play a pivotal role in mitigating stray voltage. Proper grounding practices involve establishing a low impedance path for fault currents to return to the source, minimizing voltage buildup on grounded surfaces. The use of a solid neutral grounding system ensures a stable voltage reference and reduces the potential for stray voltage. Equipotential planes, created by bonding metallic objects together, provide a uniform voltage zone and minimize the risk of electric shock. Isolation transformers isolate sensitive equipment from the effects of stray voltage, preventing interference and damage. Ground fault circuit interrupters, GFCIs, offer protection against electric shock by detecting and interrupting ground faults, mitigating the risk of stray voltage-related hazards. The role of harmonics in contributing to stray voltage is significant. Harmonic currents, produced by nonlinear loads, flow through the electrical system and can cause voltage distortion and increased neutral current. This increased neutral current leads to voltage drop along the grounding path, resulting in stray voltage on grounded surfaces. Harmonic filters mitigate the effects of harmonic currents by reducing the amplitude and preventing them from propagating through the system. Regular power quality audits help identify and address harmonic-related stray voltage issues, ensuring optimal system performance and safety. The methods for measuring and detecting stray voltage vary depending on the specific application and environment. Voltage meters, such as multimeters, measure the voltage potential between grounded surfaces and a reference point. Earth ground testers measure the resistance of the grounding system, identifying potential issues with grounding impedance. Clamp-on ammeters measure current flow in grounding conductors, indicating unbalanced loads or harmonic currents. Specialized stray voltage detectors are designed to identify and locate stray voltage sources in specific environments, such as agricultural settings. Regular monitoring and testing of electrical systems help identify and address stray voltage issues proactively, ensuring the safety and reliability of the system. The potential health effects of prolonged exposure to stray voltage are a subject of ongoing research. Some studies suggest that exposure to low levels of stray voltage may cause discomfort, anxiety, and sleep disturbances in sensitive individuals. Higher levels of stray voltage can potentially lead to more severe health issues, such as muscle cramps, headaches, and cardiovascular problems. The effects of stray voltage on livestock in agricultural settings are well documented. Stray voltage can cause behavioral changes, reduce milk production, and impaired growth in livestock. Mitigation measures, such as improving grounding systems and installing equipotential planes, help minimize the impact of stray voltage on animal health and productivity. The regulatory standards and guidelines governing stray voltage vary depending on the jurisdiction and application. The National Electrical Code, NEC, provides general guidelines for grounding and bonding electrical systems to minimize stray voltage. Industry standards, such as those developed by the Institute of Electrical and Electronics Engineers, IEE, offer more specific recommendations for addressing stray voltage in particular environments. Local regulations may impose additional requirements for stray voltage mitigation in certain areas or industries. Compliance with regulatory standards and guidelines is essential to ensure the safety and reliability of electrical systems and minimize the risks associated with stray voltage. The cost-effectiveness of implementing stray voltage mitigation measures is an important consideration for businesses and organizations. Improving grounding systems, installing equipotential planes, and using isolation transformers can be relatively inexpensive compared to the potential costs of equipment damage, reduced productivity, and health problems caused by stray voltage. Regular monitoring and testing of electrical systems help identify and address stray voltage issues proactively, preventing costly problems from developing. Investing in stray voltage mitigation measures can provide a significant return on investment by improving system reliability, enhancing safety, and minimizing downtime. Case studies of successful stray voltage mitigation projects demonstrate the effectiveness of various techniques and strategies. One example involves an agricultural facility that experienced reduced milk production due to stray voltage. By improving the grounding system and installing equipotential planes, the stray voltage was reduced, and milk production returned to normal. Another example involves an industrial plant that experienced equipment malfunctions due to stray voltage. By using isolation transformers and harmonic filters, the stray voltage was mitigated, and equipment reliability was improved. These case studies highlight the importance of addressing stray voltage issues proactively and implementing appropriate mitigation measures. The future trends in stray voltage mitigation include the development of more advanced monitoring and detection technologies, as well as the use of smart grid technologies to improve system efficiency and reliability. The use of wireless sensors and data analytics enables real-time monitoring of stray voltage levels and identification of potential problems. Smart grid technologies, such as advanced metering infrastructure and distributed generation, can help balance loads and reduce harmonic currents, mitigating stray voltage issues. Collaboration between researchers, industry professionals, and regulatory agencies is essential to develop and implement effective stray voltage mitigation strategies and ensure the safety and reliability of electrical systems.